whatever we divide it by, n squared by 1000 or whatever, it will always grow slower than that. However, 1000n is not a big omega of n squared, because big omega of n squared essentially means the lower bound, but n squared, as we know, will grow always grow faster than n. So we can think about big omega as something as an equation that is always greater than or equal to our current algorithm, right? So intuitively, it is big omega is basically greater than or equal to or the lower bound. Usually I remember it basically in the terms of that the dashes are on the lower hand side, and that basically means that it is the lower bound. On the other hand, big O is always going to be the upper bound, so that is basically the less than or equal to your current algorithm. Okay, then we have theta. Big theta basically means that we are talking about the average case of our algorithm. I usually remember this because the dash is in the middle side of your notation, but sorry about that. You can remember it as you want. It basically means that our function f of n will grow in the same boundaries defined by g of n, where g of n times c some constant defines the upper bound, and g of n times some constant defines the lower bound. So it is basically the most asymptotically tighter bound that we can have, where we have this particular equation g of n that defines the upper bound and the lower bound barring some constants, right? So f of n equals to g of n essentially means that we are talking about big theta notations because big theta notations can usually, you can think of it as equal to signs, right? But they are still within some bounds. So when we say that our particular function has a big theta of n squared, basically we are talking about the set of all functions that grow with the same order of n squared multiplied by some constant. Now, let's look at a particular example and then we'll move on to more details. So we know, so let's look at this. So n squared belongs to the set of equations of big theta n squared. Right, so because n squared has the complexity of constant of 1, we can say that 0.5 n squared and let's say 1.5 n squared are the two constants that bind n squared, right? Similarly, for n squared plus n, as what we did for big omega and big O, big theta is also n squared, right? Because, okay, let's talk about this. So we can say that a particular function is big theta or has the average case of a particular equation n squared only when the n squared equation is constant, and we talked about this last time. The equation is the same, only the only thing that we are varying is the constant. So for example, if we come back to this particular equation 100 n squared plus of n, we said that the big O of this thing is 100 n squared, right? That means that that is the upper bound, 101 n squared. But we can also say that the lower bound is going to be 100 n squared, or let's say, let's take 100 n squared, right? So we have two constants with the same equation n squared, where we can just bound this particular equation 100 n squared plus of n within these two numbers. Right? Does everyone agree that if the upper bound can be 101 n squared and the lower bound can be 100 n squared? Is
yes.
there any possible case where this is not the correct thing? What if n is negative? Although we are never bothered about negative sized arrays, that is not a thing. But even if n was negative, would this bound hold?
Yes, because it's squaring the negative number, which will produce a positive number.
Look at it carefully. Even if n was negative, would this bound hold? Would the lower bound hold? N was negative. Even if it is a squared, exactly, right? I mean, so we are in that scenario, we are subtracting a number, then this lower bound might not hold. Does everyone agree that this lower bound might not hold if we are talking about negative n? Very good. Okay, So essentially, let's always talk about positive n's. In case of positive n's, these bounds hold, right? And in these bounds, we can see that the constant is differing, but the equation is the same. That is the major thing that we need to remember in case of thetas, right? For thetas, the constants might differ, but the equation in question might be need to be the same. So n squared plus n has a big theta of n squared. Similarly, 100 n squared has a big theta of n squared. Similarly, 100 n squared plus of log 2n has a big theta of n squared. But n log n does not have a big theta of n squared, right? Because the upper bound and the lower bound do not match, right? For example, 1000n does not belong to big theta of n squared, because n squared might define the upper bound, but it surely does not define the lower bound, right? Similar to this thing, n squared might define the upper bound, but n squared does not define the lower bound of n log n, right? Similarly, n cubed by 1000, n squared might be the lower bound in this case, but n squared is not the upper bound, right? Because n cubed grows much faster than n squared. So in this scenario, n squared is not the upper bound. So intuitively, you can think about theta as being like equal, right? So within that particular part. Let me ask you a question. So can someone tell me, and since all of you guys are so good at algorithms, can some of you tell me what is the worst case complexity of insertion sort?
N squared.
N squared, very good. And then what is the best case complexity of insertion sort?
N.
N. So can we say that given insertion sort, can we say that insertion sort has a big theta of n squared? Yes. Can we say that it is a big theta of n squared? No. Why not, Brian?
Sorry, I lost my mouse on the screen. So
Yeah.
since n is the best case, then it's not bounded by
A particular equation, right?
yeah, this is the upper bound, but it doesn't include the lower bound.
Exactly, exactly. We cannot have a constant that makes both of these things the same, and so we cannot say that insertion sort has an average case. On the other hand, merge sort does have an average case, because the worst case scenario of merge sort is also n log n, and the best case scenario of merge sort is also n log n. Because what is the best case of merge sort? When all of them are sorted, let's say, right? But even in that scenario, it is going to divide your array into smaller and smaller components. So in that scenario, it is always going to take a worst case of n log n and a best case of n log n, and then we can say that merge sort has an average case of n log n. But insertion sort first basically checks for the unsorted number and then puts it back into the correct position, right? So in that scenario, if the entire array is sorted, the best case becomes n, because it just goes through the entire array once and it does not check for the smaller case anyway. So basically it is sorted. In that case, the best case is n, and so we do not have a theta of insertion sort. Okay. So that is what we usually do when we talk about big O, big theta, big omega. Essentially, we are basically comparing two equations, right? One is our functions equation, and the other equation is the thing that we are trying to bound it by. So let's talk about square root of n and log of n. So whenever you see these two equations, you need to figure out that does one function bound the other. So let's talk about the upper bound. Does log of n, so can I say that, can I say that square root of n is equal to Vigo of log of n, where log of n is essentially log base 2 of n. Can I say this? And remember, whenever you're confused, always pick some large number of n. Let's take n equals to a million. Yes, yes, Vanti, you are correct. So always take a large value of n. So let's take n equals to a million, right? And let's, for simplicity's sake, let's take log base 10. So square root of a million is going to be 1000, right? And on the other hand, we are saying that it equals a big O of, with a value of log base 10 of million, that is going to be 6. Right, so square root of n grows much faster than log base 10 of n. Right, so we cannot say that log of n is the upper bound of square root of n. We will also talk about log base 2 and log base 10n. But before we do that, let's talk about, and we will also, okay, we will talk about these things in more detail later. But think about these equations when we say that one equation can bound the other. So can log base 2n bound log base 10n? Can 2 to the power of n bound 3 to the power of n? Is it possible? Can 3 to the power of n bound n factorial? So let's think about this particular problem in more detail. So 3 to the power of n. Who says that 3 to the power of n will grow faster, and who thinks n factorial will grow faster? Type in the equation that you think will grow the fastest, 3 to the power of n or n factorial. Anybody else? Factorial? Everyone sort of agrees that this is the factorial that's going to grow faster. Okay, so intuitively that makes sense that n factorial will grow faster, but we will also look into the mathematical definition of this and how we can prove that yes, n factorial does grow faster than 3 to the power of n. But yeah, you guys are correct.
Yeah, I have a question on the insertion sort.
Yes.
We can't say that insertion short is theta of n squared, but we can say that it's big.
You got cut off. Did I get cut off or did you guys? Can you guys hear me? Hello. If you can hear me, can you just type in yes or no?